all of you. Okay, I think sufficient strength have come. Right. Good morning to all of you. Now I will start the class now. We will start discussing. Right. So this is the notes today's class notes. Right. So problems in dimension of this Macaulay method we are going to see once again. Okay. Last class I told you if you get UDL, discontinuous load in your beam, how to deal about it. The similar kind of problem you have seen. Right. Here I have a beam, timber beam, 20 centimeter wide and 10 centimeter deep. Is supported as shown in figure. Okay. Find the deflection at free and C. This is given 20 centimeter by 10 centimeter, which is the width we will see later. Okay. Find the deflection of the deflection at free and C. E equal to 10 into okay 10 kN per mm square. It's given. It's a timber beam. That's why it's below. Okay. Now this is the beam given beam. First step is to determine support reaction. Right. This is the given beam. So taking moment about A, RB into phi is equal to, you know how to determine support reaction. The support reactions are found to be reaction at A is 2.3 kN, reaction at B is 2.7 kN is found to be. Okay, 2.3 kN, 2.7 kN. So what to do, in order to write that general expression for bending moment, you have to write it in a special manner, right? Because I have already told you, the UDL, any UDL, should go up to the end. Because in this case, the UDL is up to this end. But this UDL is up to this end. Okay. If that discontinuity is there, we have to modify the UDL this way. Okay. The load diagram is to be modified. This one only we have to modify and write the general expression. So the same beam I have drawn. I have taken UDL fully. This 1 kN per meter. I have taken fully. Okay. Then I have applied 1 kN per meter upward fully here. So what happened for this portion? It is get cancelled. Okay. So empty. Here empty. Here no UDL. So downward UDL, upward UDL get cancelled here. Okay. So it is equal to the top, this. No problem. For the portion dV. Okay. When it comes to here, the UDL get cancelled, isn't it? But a 0.5 kN per meter acting downward here. That is why this is UDL. It's not a striked out. Don't mistake and here I striked out. No, it's a UDL. It is a UDL superimposed. Another UDL is acting here. Whose magnitude is 0.5 kN per meter. Okay. So all UDLs are starting from one end. That is the important thing. Either from the left end or from the right end, all UDL acting on the beam should start. Okay. So that is why you have to modify the load diagram this manner. This load diagram is equivalent in action with or is equal to this load diagram. Okay. This special manner we have to draw it, right? Modified manner. But without affecting the effect of the load on the beam. Okay. We have not changed the effect of the load on the beam. This simple modification we are doing it in order to write a general expression for bending moment. The parts of the terms will be applicable to each portion. For that purpose, this kind of a special procedure or special manner we proceed. We do it. Okay. For that, more practice required. You have to practice several problems from textbooks. Right. So I have taken A as origin. Right. I am considering the far away portion. Far away portion is BC. A section XS at a distance X from the origin E. Okay. I have considered a section XS at a distance X from the origin E. Right. Now, according to Macaulay's method, the general expression for bending moment can be written in special manner. Right. That is mx is equal to, I am writing mx, moment at the section xx is equal to the support reaction 2.3 into x, the section is at a distance x from the A, x, okay, minus, because upward moment with upward is positive, next minus, here in this portion UDL is there, see here, in this portion UDL is there, that is why it is 1 into, what is that, 1 into x square, you have to refer this flow diagram, no? You have to refer this flow diagram. So the UDL is acting, 1 kN is acting throughout the length of the beam. The moment produced by this UDL about x is 1 into x by 2. That's why 1 into x square by 2. Okay. This bending moment expression is applicable for portion AD. The first, this is called first part. It's last class I used the word term, first term, second term. That word I have used. I want to correct it now. Okay, it's not term, part, right? This is the first part, second part of this equation. See, a part maybe consists of several terms in it, right? So first there are one or two terms in it. So it's a part. This first part is applicable for first portion, AD, right? Because if you write general expression for bending moment, this will be the general expression for bending moment in the portion AD. That is why you have to put the dotted line here, right? And then we are coming to the side part of the bending moment, general expression for bending moment, right? So next, this support reaction is over, this UDL is over. Okay, now we are coming to this 1 kilonewton. This 1 kilonewton is acting vertically downward. So that is minus. Okay, minus 1 into x, from here it is x, here it is 3, no? From A level 1 kilonewton is at 3 meter. From A, the section x axis is situated at distance x. Okay, that's why x minus 3. 1 into x minus 3 I have written. Okay, the moment. That alone is in this portion dB, not only 1 kilonewton, there is upward UDL is also acting. Okay, that is since it is upward plus sign, plus the upward UDL is 1. 1 into, okay, what is this one? The section is here, no? 1 into, how do you write? X, from here it is x minus 3. That is the spreaded length of this one. Okay, because the section axis is here, the spreaded length of the upward 1 kilonewton UDL is how much? 1 into x minus 3, right? So this one into x minus 3 divided by 2. From the axis x-axis to its center of run. It's okay, center, it's located. Center of its run is located of this upward UDL. Okay, left part of the upward UDL with respect to this section, right? That is x minus 3 4 squared by 2, right? Next, that is over, right? Actually, we see here for the portion dB, support reaction, this one, this UDL, this portion is over. That's why you write here dotted line here. Okay, dotted line we are not putting here. We are putting here. Please keep it in mind. Yes, this part. This is the side part. Okay, for first part, this much for first portion, first part of the equation is applicable. For second portion dB, the first part and second part of the expression is applicable fully. Okay, first part and second part of the expression is applicable. Now I am coming to the portion BC. For portion BC, you have to include at this section the UDL, which is acting upward first. Okay, so which one we have done? Upward first. Okay, the support reaction. The support reaction acting here, which is 2.7. 2.7 into x minus 5. Okay, 2.7 into x minus 5. That is the upward reaction. Then there is a upward UDL already over. There is a downward UDL acting. Okay, this UDL is over. This UDL is already included in the first term or second term. Only the 0.5 UDL is acting downward. That will be upward to be included, which is minus 0.5 into x minus 5. From here it is 5. No, the distance between support A and B is 5. UDL starts only here. No, so x minus 5 into x minus 5 divided by 2. That is why x minus 5 whole square divided by 2. Okay, like this we have written general expression for bending moment, but we have divided this into 3 portions, 3 parts, because our beam is divided to 3 parts, right? I'm not supposed to use the word terms. First 3 terms I am not supposed to use. First 3 portions, first 3 parts of the equation. Okay, so we have divided this general expression for bending moment into 3 parts. Okay, with by take dotted lines here. You are considering the first part is applicable for the first portion AD of the beam. First and second part both together applicable for the portion dB of the beam. First part, second part, and third part all together applicable for portion BC of the beam. That is the meaning of it. Okay, in a special manner we are expressing bending moment, and also in a special manner we are expressing the loading diagram. Please keep everything into mind, right? Now we are carrying out integration. EAT square by ds square is equal to because that is equal to minus. I have written. Okay, this plus become minus or minus become plus here. Like this, we have written the equation. Okay, by changing the sign because we know d square by ds square equal to minus m. Okay, I have written here. Now I am carrying out integration. Here dy by dx is equal to you know how to carry out integration. We are including the entire constant here. Okay, the first part of the equation, first portion of the equation, or first part of the equation, and not first term. Okay, the word which I used term is not appropriate. The first part of the equation, first portion of the equation, we are including this just before the dotted line, the inner constant C1, and then we are carrying out integration also in a special manner, as I told you. Wherever this kind of x minus 3, x minus 5 and all comes, square, okay, divided by 2, cube divided by 6, like that, cube divided by 3, like that we are doing it. 2 into 3, 6 it becomes here. Okay, so this way we have carried out integration also in a special manner. Already you are aware of it. I need not explain in detail how to carry out integration once again. Okay, it's not necessary. Then I will go to integrating again. Okay, so we are the integral constant C1s plus C2. The integral constants are included in the first part of the equation. Okay, here just before the dotted lines, right? And the remaining part, the integrations are carried out in a special manner, as I told you earlier, right? Now we have to evaluate the integral constant. For that, we are applying boundary conditions. There are two boundary conditions available. So that is at the support E. It means that x is equal to 0, the direction is vertical direction y equal to 0. The vertical direction on the beam is 0. At x is equal to 5 means at support B, the vertical direction of the beam is 0. These values are known to us. They are called boundary conditions. Okay, we have to apply this boundary condition, which implies C2 is equal to 0. Then we are substituting the y equation. Y equal to 0 and x is equal to 5 in this. To substitute, we are getting C1 is going to be 4.24167 number. Okay, numerical values. Okay, diffraction at the free end. I want to determine diffraction at the free end. But if you want to determine diffraction at the free end, what is the value of x? Origin is chosen A, no? From A, the x is measured. Okay, that's origin is A. We have in our general expression, we have chosen like that. That is why substitute x is equal to 7 meter in the equation. Why? This is substitute x is equal to 7 meter, and the C2 value already I have determined, no, C1 value. That also is substitute. Now, if you substitute everything, and if you do the computation, the maximum deflection or the deflection at the free end is found to be 3.01 centimeter. That is 30 mm, almost 30 mm, 1 feet. It is found to be. So the beam deflects that much, considerably deflects. Okay, at the free end, the beam deflects that much here. Okay, so this is the way the problem required to be solved. This way we are doing the problem. Okay, because the overhanging is 2 meters. See, overhanging and 0.5 kN is acting. Moreover, the loads are away from B here. That's why it's not able to counterbalance the deflection here. So the deflection is considerable here in this problem. Okay. So why I have got this problem? Just to tell you how to deal with UDL and all by Macaulay's method. Problems are plenty. I advise you to practice it. Okay. Right. So next one, similar kind of problem. In addition to this UDL, similar problem. In addition to that, a couple is acting here. You know how to you have to modify this load diagram like this. Okay, full UDL and then upward UDL of 0.5 kilonewton and then additional UDL of 0.5 kilonewton downward. Okay, and you can deal it. Only thing is the moment is there. With couple act, how to include couple in the general expression for bending moment. You have already studied in your mechanics of solids. Okay, that is a mechanics of solids. How to deal with the couple? How to include it in the general expression? Okay, if it is anti-clockwise, positive, clockwise, negative. Okay, not only that, we will see how the beam tends to bend. That also we will see. Okay, that's all. This way the problem can be done. There are plenty of problems. Just I have drawn some loading diagram here. Mechanical of direction of beams. There are other problems I have given. This is a similar kind of problem already we have seen. Okay, we have a simply separate beam, only a portion UDL is acting. How to deal about it? The UDL is taken fully, and then here there is no UDL, no, so upward UDL. So it's get cancelled. That's why the beam will be free here. Okay, the UDL should be run to up to any one of the end. Likewise, you have to modify the load diagram and write the general expression and deal it. This problem already we have seen in the Punya textbook, I think. Right? Next, yeah, similar problem. Just now I told you. This way is required to be modified. I have not done it. Just given some hints. That's all. Not necessary. Because in the textbooks there are plenty of problems available. Right? I advise you to go through those problems. You have to because mechanism method. That's all. And then some simple problems are like that. There are several problems available in textbook. I don't know from which book I have taken this problem. Most probably I might have taken from Punya or Vajra Datvani, right? A simply supported and uniformly loaded wooden beam of square cross section has span of 3 meters. Find the maximum deflection if the maximum bending stress is 100 Newton per meter square. Similar problem already I told you. Same problem. I think same problem, not similar problem. Same problem I told you. Okay, how to do it. Fully supported beam, uniformly loaded wooden beam of square cross section. Please recall, already I told you. You have to determine what is the dimension of the beam. How do you get? M equal to F into Z. Okay. What is Z? Z is B square by 6. That is B, because it's square section. Okay. So depth is nothing but width. So B Q by 6. Okay. Z equal to B Q by 6. F is given, which is 100 Newton per square. M you can compute. M you can compute in this, right? W is given, UDL is given, span is also given, W is square 8 is given. Okay, from this we can determine the P, the width of the beam and depth of the beam can be determined because it is square section. Once the dimension will come to know, from this we can compute I. I equal to BD square by BD cube by 12, BD cube by 12, you can determine. Okay, I you can, because of B you determined. D is nothing but D. Okay, B cube by 12, you can determine I here. And then you can compute deflection. What is the deflection? It's a UDL, no? So what is the deflection? Deflection is maximum of the center. What its value? 5 WL power 4 divided by 384 EA. That you have to substitute all the data is determined. And you will be getting 1.268 centimeter the deflection. This way, this problem, you have to solve the problem this way. Okay, just I am giving hints because this problem already you have seen. That's why I am just brushing up or speeding up, right? Next, a simply supported beam of 10-meter span. It's not that, okay, a simply supported beam of 10 meters span is carrying a point load of 100 kilonewton at 6 meters from the left end, right? Calculate the deflection under the load. Take E equal to 0.2 Newton per m square and I equal to, okay, 1 lakh centimeter power 4. Okay, answer is given, right? So how do you go about it? You are asked to determine the deflection at the under the load, right? So how do you do that? Draw the beam, draw the point load, 6 meters from the left end, 10 meter span beam. So you consider any portion. First portion you consider, write the general expression for bending moment. Okay, carry out integration twice, right? So write general expression for bending moment for the first portion. Take A as origin. Okay, carry out integration twice. Then you apply boundary condition, evaluate the integral constants. After evaluating it, what you do? You will be getting final equation for deflection. Okay. In that equation, substitute x is equal to 6 meter because under the load you are asked to determine load, the deflection. Okay. The load is 6 meter at a distance 6 meter from A. That's why substitute x is equal to 6 meter. So you will be getting the deflection. Okay. You will be getting the deflection there. Calculate the deflection under the load EI. That's what it is given. Because you have EI value no in your Y expression. EI Y is equal to you will be getting EI value also given. So it is found to be 0.96 centimeter. That is 9.6 mm. Right in this problem. This way you have to solve this problem. Next step. Determine the maximum. At least I advise you to take some paper or something and note down because I want to start the rest method, moment area method. That's why I am rushing. Okay. I don't want to spend. This problem comes under some problems are from like a double relation method, McCall's method. Okay, if only one load, single load actor, we call it as double relation method. If several discontinuous load actor, we call it as McCall's method. A special manner we are carrying out everything. No, that's why it's called McCall's method. Okay, I want to finish up that method by today. I want to start the next method, moment area method. That's why I'm telling you how to solve this kind of problem. Next, determine the maximum deflection of a simply supported beam of 10-meter span carrying a point load of 100 kilonewton at 6 meter from the left end. This is 100% similar to that of previous problem. Okay, similar to that. Only the thing is, same problem repeats. Yeah, same problem repeated here. No problem. Same problem. I have written the problem twice. No problem. Next, likewise, problems are 20. Okay. A simply supported beam of span 10 meter is loaded with the uniform distributed load of. Yeah, here a simply supported beam of span. What the difference between this problem and that problem? Any difference is there? No, I told you. Yes, determine the maximum deflection of this simply. Oh, in this problem, yeah, they are similar problems, similar load diagram. Here you are asked to in this problem, you are asked to determine the deflection at the under the load. In this problem, you are asked to determine the maximum deflection in the beam. Okay, so that is the difference between these two problems. Both are the same loading diagram, same the beam, same point load is applied. Here you are asked to determine the deflection under the load. In this problem, you are asked to determine the maximum deflection. How do you do that? We know at the maximum deflection point, the slope is 0. d over dx is equal to 0. So equate slope equation to 0 and determine what is the value of x. If the value of x within this 6 meter, it's okay. The maximum deflection occurs in the first portion. Suppose the x you are getting some irrelevant answer. What to do? You have to write general expression for bending over the next portion. Okay. Now the beam is divided into two portions. No, because point load is acting at the somewhere 6 meter from the left end. Okay. So A to B, say support A, support B, and where the point load acts, say C, AC. You are written general expression for portion AC. Okay. That in that you have slope equation. Equate that to 0. If the x value is within 6 meter, it's good. The maximum deflection occurs there. If not, you have to write general expression for next portion. Okay, that is CB portion. Okay, in that you determine what is d over dx. Equate that x equation to 0, that slope equation to 0, and determine what is the value of x. Okay, you have to verify. But it is obvious here from this problem, the maximum deflection will occur within 6 meter, no doubt. Okay, so this way you have to solve this problem. What is the next problem? A simply supported beam of span 10 meter is loaded with a uniformly distributed load of 5 Newton meter over here, length of 3 meter from the left end. Find the maximum deflection of the beam. Okay. All the other structural rigidity values are given. E value and I values are given. Okay. You know how to do this problem. If any UDL is acting, you know how to deal. Okay. How to go about it. This already you have learned very well. How to modify the load diagram, how to write the general expression for bending moment in a special manner, and how to proceed. You are already thorough. I you know that this problem is given with numerical values, you will do it. Okay. Now only point loads. Consider the last portion. Now the beam is divided into four portion because there are 3 point load act on it. Okay, that's why the beam is divided into four portion. Take the A as origin. Take the last portion. Consider the section XX in the last portion at a distance x from A. Now you write down the general expression for bending moment for the last portion. Now the general expression is divided into four parts. Okay, four portions. Right. Now what to do? You integrate once, twice. Write down apply boundary conditions. Evaluate the integral constants. Write down the final equation. Okay, for deflection as well as for flow. Right. Now you are asked to determine maximum deflection. We don't know where the deflection will be maximum. So suppose normally it will occur at midspan. Okay. Suppose you are feeling the maximum deflection occurs between portion, 40 kilometer and 20 kilometer, you feel, you just suppose. Equate that first two part. Okay, equate first two part to the slope equation of first two part to 0. Determine what is x. If the x lies within this portion, good. Between maximum the part of the slope equation and determine what is there. If your x value is well within this portion, it shows that the x value is substituted in the slope equation by considering the three parts. Either two or whom I am dealing. Okay, but one minute. Just I will check up. Some again, I will move some students so that it will be well recorded. No, I will move like this the name list. So I will keep like that. Next method. Called the most method.
Class over.
What happened? Why it has come out? It's okay. Now, am I audible to all of you? Is it visible? Yes. Rahul, audible? Am I audible to all of
Audible,
you?
sir. Yes, sir.
Again, you seem to know? No problem. Okay. I will keep like this. For the purpose, I will just keep. Okay. Now it is visible now for all of you. Shall I proceed?
Screen, sir. Screen, sir.
Visible now?
No, sir.
No, no, screen sharing will record. Oh, I read it. Screen sharing is not done. Presentation. Uh, oh, somebody might have, some student might have shared their screen. That's why it got disturbed.
Now visible, sir.
Please, all of you keep it in mind. Boys, girls, please keep it in mind. If any one of you by mistakenly share your screen, what will happen? My screen will go. My sharing will go. Your share will come. Okay. That is the problem with this Google meeting. That cannot be banned. Okay, your activity cannot be banned as we ban in Zoom software. Here, if any one of you by mistake share your screen, please don't operate a share in your mobile or in your laptop, right? Don't touch that button share, right? If you do like that, mine will go, yours will come, your presentation will come. That is the problem. Your cell phone page or your screen will come there, right? So don't do present that. Don't present your this one. Now it is visible now. Notes visible now. Rahul, notes visible. Am I audible to all of you?
Visible, sir. Audible and visible, sir.
Audible. So
Yes,
it's
sir.
okay.
Visible, sir.
Yeah, yeah.
Sir.
Commodity method. It is a very interesting method. I will finish it. Another 10 to 15 minutes I will be discussing. Please see here. It is a very interesting method. Using this method, you can determine the deflection or slope at any required point. Right? I will read it here. Moment area method is the another method for finding deflections of beams. Okay. It utilizes properties of the area of the bending moment diagram. Okay, no doubt. That's what it's called moment area method. This method is especially suitable when the deflection or the angular rotation at only one point of the beam is desired, because it is possible to find those quantities without first finding the complete equation of the deflection curve. Okay, that's what. Now, what I have done, I have considered a deflection curve here. Please see here, just record purpose, I will keep the student name like this. I have considered deflection, a portion of a deflection curve of a beam. You consider the cantilever beam. Very initially, we consider the cantilever beam, no, it was deflecting. Some portion, AB, of the deflection curve. It is the, if the curvature is downward, it is called the right. In the I am considering a portion of the beam AB, in which I am considering the elemental length of the beam. Okay, I named this point as M1, M2 at a distance ds along the curve. Okay, ds along the curve. Now what happened? The angle subtended by this point M1. You draw the normal to M1 and M2. The angle subtended at the center of curvature is d theta by these two radial lines, by these two normals. Okay, d theta, normal to the curves. Okay, it has subtended an angle d theta at the center. Right. Now what I have done? I have drawn tangent to M1 and tangent at M2, right? Two tangents I have drawn, tangent at M1, tangent at M2. The angle between them are d theta. Why? The angle between the normals to the M1, M2 are d theta. Obviously, if you draw tangent to M1 and tangent to M2, the angle between them will be d theta, no doubt. Because angle between two lines are d theta, the angle between their normals are d theta, right? Because this is normal to, okay, I hope you will understand. Normal to M1, this is normal to M2. The angle between them is d theta. Therefore, angle between their perpendiculars are d theta. Perpendiculars are nothing but tangent at M1, tangent at M2. The angle between them are d theta. Okay, that is one thing. Another thing is, they are considering a portion of the beam between AB, no? Here, some considerable portion of the beam AB, elemental portion of the beam AB, right? Draw a tangent at A. This is a tangent at A. This is tangent at B. I have drawn a tangent at P here, right? The angle made by this tangent with the horizontal is theta A. Say, I have drawn a tangent at A to the curve. The angle made by this tangent with horizontal, this line is horizontal line, is theta A. The angle made by the tangent at B with horizontal is theta B. Okay. Now I am taking this tangent here, go and meet the tangent at A here. Okay. The relative angle between tangent at B, the relative angle between tangent at B with respect to the relative angle of tangent at B with respect to tangent at A is termed as theta B. Here I have termed. Okay, it is nothing but the relative angle of tangent at B with respect to tangent at A. Please remember, this is the tangent at A. So the relative angle is theta B. Okay, or the angle between tangents are theta BA. I termed it as theta BA. That alone, not only that, I also have done some vertical offset here, right? Vertical offset. So please see here, I have drawn two tangents to point M1, M2 go. The vertical offset here is P1, P2. Between the point P1, P2, I termed it as D del. D del. Okay. Next, the vertical offset of the tangent P and it's up to the tangent at A. I termed it as del B. It's called vertical offset. Please see here, the vertical offset of point B, vertical offset of point B okay, from tangent at A. This is a tangent at A. Then we have termed this same point as B dash. This vertical offset is del B. Okay, something we have done, some drawing we have drawn, some diagram we have drawn. Not only that, below this beam, I have drawn a bending moment diagram of that beam. Okay, the bending moment diagram, you know how to draw bending moment diagram, M diagram, called the bending moment diagram, M diagram. In addition to the bending moment diagram, what I have done, each and every ordinate of the bending moment diagram, I divided by the flux rigidity EA. That is called M by EA diagram. That is called M by EA diagram. Each ordinate of moment, I divided that by the flux rigidity EA of the beam. That's what it is called M by EA diagram. So this shaded portion shown the area of the M by EA diagram between the portion AB. Here, I have projected this point M1 and M2 here. I have shaded another matter. This elemental area, the shaded portion of the cylinder area shows the area of M by A diagram for the elemental portion M1 M2. Okay, M1 M2 for the elemental length here. Okay, let us see. This is the diagram we are referring. Okay, with respect to this diagram, I am going to discuss something with you. What is that? To explain the method, let us consider a segment. Sorry, this is elemental length. This is called segment AB. Okay, that's appropriate word, segment. To explain the method, let us consider the segment AB of the division curve of a beam in a region where the curvature is positive. Okay, in a region where the curvature is positive. Okay, we have considered. Right. Next, the angle between the tangent theta BA equal to theta B minus theta A. Theta B minus theta A will give you theta B. The angle between the tangent, okay, the angle between the tangent, you can say R, the angle, the relative angle of tangent at B with respect to tangent at A is equal to theta BA, which is nothing but theta B minus theta A. Okay, which is equal to theta B minus theta A. Relative angle also we know. Relative angle between the tangents we know very well. Okay, that also we have defined or expressed. Thus, theta BA represents the relative angle of rotation of the tangent B with respect to the tangent at A. Okay, so theta BA represents the relative angle of rotation of tangent at B with respect to the tangent at A. It's okay. Next, consider 2 points M1 M2 on the axis of the beam at a distance ds apart. That also we have considered already. Now, this already we have got this differential equation of division curve we have derived. No, that time we got d theta by dx is equal to d square y by dx square is equal to minus m by a. This relation already we have. From this only we got d square what is that? EI d square y by dx square is equal to minus m. We got no. So in that we got dx by d theta by dx is equal to d square y by dx square is equal to minus m by a. This relation, this since already we have this. From this I am writing d theta is equal to minus m by a into dx. Minus m by a into dx. Equation 1. What it means? This arc length. Okay, that is okay. This already we have got. I may not explain now. This already we got. We have this already in the differential equation of the division curve. We have there, you know, that time we got this relationship. Theta is equal to theta is nothing but ds. Sorry, dx is nothing but ds here. Okay, d theta is equal to minus m by e into dx. Okay, equation A. Directly below the beam, we draw the M by EA diagram, right? That is a diagram in which the ordinate at each point is equal to the bending moment at that point divided by the factor EA at that point. Okay, this already just now I told you. Right. I will finish. Another 5 minutes only I will be discussing. Okay. The term M by EA dx is the area of the shaded strip within the M by EA diagram. What is the M by EA into dx? What is M by A? This is M by A into dx. Okay. So I am projecting this one vertical. Right? So this vertical horizontal direction, the distance is ds. Along the curve it is ds, but in the horizontal direction it is ds. So M by A into dx is nothing but the shaded area here. Okay. On the bending moment of curve. That also that's just given. Let us now integrate equation A between point A and B. Now I am going to integrate this equation A between point A and B for the segmental length of the beam. Let us see what will happen, right? So if you integrate integral A to B d theta is equal to minus integral A to B m by A into dx. Okay, this we are integrating for the segmental length of the beam A to B. Okay, we are integrating it. That is the equation B. So what is that left one? The integral on the left is equal to theta b minus theta e. If you integrate d theta, you are getting theta. If you substitute upper limit and lower limit, theta b minus theta e, which is nothing but relative angle of rotation of the tangents. Okay. So we are getting theta b minus theta e, which is the relative angle theta b between the tangents at B and E. Okay. The integral on the right is equal to the integral on the right, this one, is equal to the area of the M by A diagram between the point A and B. So here we are getting what is minus integral A to B M by A into ds is nothing but the area of the M by A diagram between A and B. Okay, that's what it gives. That is equal to, therefore V implies theta BA is equal to minus integral A to B M by A dx, which is nothing but minus area of M by A diagram between A and B. Okay, close the bracket. Area of M by A diagram between A and B. Close the bracket. Which one? The relative angle of rotation between the tangents, theta BE. Now, from the geometrical property, we are getting this kind of equation. Okay, expression. This equation may be stated as follows, as a theorem. Okay, this equation may be stated as a theorem. That is called a first moment area theorem. Please, all of you remember, first moment area theorem. The angle, if you don't like the relative angle of rotation, you can write. Otherwise, the angle theta BA between the tangents, okay, to the diversion curve, between the tangents to the diversion curve at 2 points A and B is equal to the negative of the area of the M by A diagram between those 2 points. Okay, those points. So first, the first moment of area theorem states you have a diversion curve of a beam. You take any 2 points on the curve. Okay, the relative angle of rotation between the tangent at those points is equal to the area of the M by A diagram between that point. That's what the first moment area theorem says. Okay, the first okay, that is called first moment area theorem. The relative angle between 2 points. I will repeat, the relative angle between the tangents. In other words, the relative angle of tangents at 2 points A and B. Relative angle of what do you say? Relative angle of tangents between 2 points A and B is equal to the area of M by A diagram between that 2 points, those 2 points. Okay, that's what the statement says. But it is given in a different manner. That is theta B with the notation. The angle theta B, instead of saying relative angle of rotation, is given the angle theta B between the tangent to the diversion curve at 2 points A and B is equal to the negative of the area of the M by diagram between those points. I forgot to include that negative. Okay, that's important. Negative of area M by diagram. If your curvature is upward, you will be getting positive. So since we have taken sign convention like that, negative, right? This is called the first moment of area theorem. Next, we are going for sine moment area theorem, right? Shall I stop it now? Because we may get this was sufficient. Because it's next class I will continue. Okay, time is almost time 18. I will keep some name like this so that it will be well recorded for attendance. Your name will be registered well for attendance. Okay, so I want to take attendance purpose. Just I want to move your names like this, right? I'm just recording attendance because I will send you the notes very by possible by today. Okay, you go through, then only you will understand. Whatever I explained, keep it in mind and go through the notes deeply, especially this derivation. It's very easy. Its application will be very interesting to you. Now it may confuse you. Why are discussing so many things like that? It may confuse you. Later you will understand, right? So I have recorded your names for attendance purpose. Your names have been well recorded, right? Well recorded. Your names are being recorded. 2 minutes. I will take attendance, right? recording your names. I have recorded your names. Oh, camera is not working. It's working, okay. So, what about you? Yeah, please, because it's derivation, this is a diagram I confuse you. It's okay. I will send you the notes. Go through. Okay. Only for up to first moment area theorem, I told you. The remaining part you will see in the next class. Okay. Next class I will explain. I advise you already. Yesterday I have sent you the Dr. B.C. Punya textbook as well as Bobby Getty. Sorry, not Bobby Getty. R.K. Bansal. Both the textbooks I have mailed it to you. I advise you to download those books. Okay, soft copy already I mailed it to you. Please download them and take some problem and work out. Apply your mind. Unless you apply your mind, you can't learn by just by listening to me. My teaching will just help your self-learning process. It will simplify your self-learning process. That's all. You have to apply your mind and learn. Not only my subject you are learning, there are other subjects. Each subject you have to study systematically. Okay. There are six theory subjects you are studying this semester now. Five or six you are studying this semester. You have to study the portions taught are covered by the teachers systematically. Every day you have to sit and study. Then only you will follow the next class. Okay. Especially this kind of problem. If you want to follow some class, you should be thorough with what we have learned, discussed so far. Right? I will try to send notes by today. Whatever I taught you from the first class, I will send the notes to you by today and mail you. Please study periodically, systematically. Okay? Not only my subject, every subject. But especially this kind of problem related subject, you have to study systematically every day. Okay? Then only you can follow, right? So with this, I will few minutes. Just I will stop recording. Then we will discuss. If you have any general discussion, we will do. Okay. I will first stop.